If you think all the way back to chapter 2, we talked about average velocity. We said average velocity was distance traveled, divided by the time it took you to do that traveling. But now in chapter 5, we have a new way of computing distance traveled. We say it's the area under the velocity curve between two time limits, which we can model with a definite integral. So no, I noticed that I can take that same idea that I had in chapter 2, I just have some new ways to write some of those things. And I can write the average velocity is 1 over b minus a times the integral from a to b of v of t dt. So that's the same as saying the distance traveled, that's the integral part, divided by the time it took you. That's the difference between the two time values. And it turns out that this idea of finding the average value of a function applies not just to velocity. So we're going to use that in lots and lots of different places, lots of applications, and it's so important that there's a place on your 19 facts paper for you to write an expression for the average value of a function. We're going to practice here in this next example. And so we're going to practice average value of a function with this example here. So I'm told I have a metal wire. So I drew a metal wire here, blue wire. It's 8 centimeters long, and I made this red because this is like a fire or something attached to the wire that's heating it up, and the heat is coming from this end where the fire is. So however hot it is at this end is the hottest. In fact, I've been told specifically the temperature function is decreasing. So as the length of the wire, as the distance from the heating element increases, the temperature decreases. So that kind of makes sense. It's hottest here, it's less hot here, it's less hot here, and it's less hot here. And at the very far end, the end that's not near the heat source, the wire is the coldest. And these are the temperature readings along the wire in degrees Celsius. So I've been asked to write an expression in terms of T of x for the average temperature of the wire. So remember, average velocity was 1 over b minus a times the integral from a to b of velocity. Well, we're going to have 1 over b minus a times the integral from a to b of temperature to get average temperature. Only problem is we're going to have to figure out what a and b are in this case. So we've been told that the whole length of the wire, 8 centimeters. You can even see here I have a temperature reading at distance 0 and a temperature reading at distance 8. So I'm going to use 0 and 8 for my. So here's part 1, the first part of the part B question, which is, can you write an expression using T of x in your expression for average temperature? It's going to be 1 over b minus a, but that's 8 minus 0, times the integral from a to b, so from 0 to 8, of T of x dx. And you can compare that to what you have in your notes for average value of a function for what I wrote somewhere along here, which was for average velocity too. Okay, that's great. If you wrote that expression, you got 1 point already. You get like 70 points and you get a 5. So let's see if we can answer the next part of the question. Estimate the average temperature of the wire using a trapezoidal sum with the 4 subintervals suggested by the data. So this is an expression that has an integral in it. If I could really graph the t function and find the area under it, then I would know the exact answer for the average temperature. I don't. And since I only have specific points along the t-axis, I'm never going to, along the t function, I'm never going to actually know the real function. If I know the real function, I can do some cool stuff that comes up at the end of this section and maybe try to find the real answer. But right now, the best I'm going to be able to do is make an approximation. So notice that we can use everything we learned in 5.1 about Riemann sums, in this case, a trapezoidal sum. So I see 1/8 times an integral. So that's going to be approximately equal to 1/8 times. I can use an approximation for that integral, and I've been told specifically to use trapezoids and to have them cover the interval from 0 to 1, from 1 to 5, from 5 to 6, and 6 to 8. So I'm going to write in my expression for, notice I need the 1/8. We didn't see that part in 5.1 because we'd never had an average value situation. But that's where the 1/8 comes from. And now I'm going to approximate this integral using a trapezoid sum. I'm going to come down to the next line so I can write it all out without having to break my line. So remember, for a trapezoid sum, I'm going to need to add up the areas of a bunch of trapezoids. Specifically, I've been told I'm going to have 4 trapezoids. So if you want to write this out before you even start, you can. Right? Make sure you have parentheses or some kind of grouping symbol for this 1/8 because it would have to get distributed. So how do I find the area of a trapezoid? Well, it's going to be the average of the parallel sides. In this case, our trapezoids are standing up on their side. The parallel sides are the 2 heights. So I want to find the average of the 2 heights. I'm going to multiply by the width. The width is the distance, the change between the input values. So in this case, between the x values. So I'm going to multiply. My 2 heights are 193, so I'm going to take their average. That's 100 plus 93 over 2. I'm going to multiply that by the distance between 0 and 1 is 1. For my next trapezoid, my 2 heights are 93 and 70, so I'm going to take their average, 93 plus 70. Taking the average, that's adding them together and dividing by 2. I'm going to multiply by the width of that trapezoid. Well, that trapezoid covers x values from 1 to 5. That's a difference of 4. For my next trapezoid, that covers from 5 to 6. My 2 heights are 70 and 62, so 70 plus 62. I'm taking their average. I'm going to multiply by the distance across that interval is 1. Obviously, if you left that 1 out, it doesn't affect the result, so you wouldn't lose any credit. I want to put all the numbers in, so when you look back at this later, you can sort of compare it to where these numbers came from and understand better. And my 4th trapezoid, I'm going to average the 2 heights. That's 62 plus 55 divided by 2. And the distance across that last trapezoid is the difference between 6 and 8, which is 2. It's the AP test. Feel free to leave your answer like this. I would, I would go ahead and expect that with numbers like this, that this came from a calculator active problem. There's sometimes where they'll ask you to do a trapezoid sum, and it won't be a calculator problem. You don't have to simplify your result. You could, and the numbers will be a little more round, so it would come out a little faster. So I'm going to use my calculator and simplify this expression. All right, so when I used my calculator on that, I notice here it was number 5. If it were a number 5, it never would have been a calculator problem, but this was a calculator problem. When I went to double check my answer, it's really number 3. So that was 1/8 times the integral from 0 to 8 of t of x dx is approximately equal to 1/8 times, was that 605.5? Which is equal to, what, 78, 76, 75.6875. So let's talk about units. Let's talk about how to tell if your answer is definitely wrong. Here's what you need to know. The number 1 most common wrong answer to this question, I would bet $100, is 605. Because people forget this 1/8 part, and they're so busy trying to compute that trapezoid sum that they finally get the answer 605.5, and they're so excited that they forget to then divide by 8. So here's what I need you to know. If you got the answer 605.5, and then you read back to the problem and say, estimate the average temperature of the wire. You have a wire, it's 8 centimeters long. The temperature at one end is 100. The temperature at the other end is 55. Is the average 600 degrees? Well, the average has to be somewhere between 55 and 100. Now, I'm not saying it's the exact average of those 5 numbers added up and divided by 5, but it's got to be somewhere in there. So if you got an answer of 605, you know something's wrong. The first time I did that problem, I paused the video and I was doing it on my calculator, I got 37. And I had to say to myself, the answer cannot be 37. And I had to go back and find out what it was. And it turned out that this this trapezoid that covered from time 1 to 5, I had forgotten to multiply by 4. I had just taken the average of the two heights. I hadn't multiplied by the 4. So I need you to be checking your answers like that to make sure that the answer you get really feels like it could be the average of the values. Even though you're missing most of the values, but does it kind of feel like it really could be the average of the values? Does it seem like the average value of the temperature, the average temperature of that wire could be 76 degrees? It kind of seems like that makes sense. So the next thing we have to talk about is units. So your units should make sense. So feel free to ask yourself this question: what do I think the units are on average temperature? Well, temperature is measured in degree, in this problem at least, in degrees Celsius. So this is in fact degrees Celsius. How could you prove that that's right? Here's one way to do it. This one, I'm looking at this expression here. 1/8 is 1 over 8. It came from 1 over 8 minus 0. And notice the 8 and the 0, they were time. No, that says cm for their distance units. So this is 1 over 8 centimeters. It's bumped up against an integral. That means multiply by. And look what's inside the integral. The integral just means add up a bunch of, right? And we use trapezoids to approximate it, but this integral represents using infinitely many rectangles. So think about what the areas of those rectangles. They came from height times width. Well, the heights are temperature values, and temperature in this problem is degrees Celsius times and a tiny change in x. Well, the x's, the inputs in this case, are measured in centimeters. So I get 1 over centimeters times degrees Celsius times centimeters. So there's centimeters, there's centimeters. So I get that degrees Celsius. Or you can think about what you wrote, the trapezoidal sums. This 1 over 8, it's still 1 over centimeters. And then every trapezoid that you wrote, it was an average of temperatures, right? So an average of the two heights, and those heights were measured in temperature. So the average of two temperatures is still a temperature measured in degrees Celsius. And you got multiplied by the distance across the width of that trapezoid, which was measured in centimeters. So 1 over centimeters times degrees Celsius times centimeters gives final units of degrees Celsius.